Hey guys, welcome back to my channel, and in today's video we are going to solve one more LeetCode question, that is question number 876, middle of the linked list. So this is an easy level question which has been asked by these many companies in last 2 years. So let's see what this question is all about. So in this question we are given a head of a singly linked list or a single linked list, and we have to return the middle node of the linked list. So if there are two nodes or two middle nodes, then we have to return the second middle node. Now if we see these examples, so in first example there are 5 nodes, so we can easily find the middle one, which was 3, and returned it. And if we see the second example, so we can see that there are 6 nodes. So if we are going to calculate the middle node, we will get two values, that is 3 and 4. So we have to return the second one. That's why we return 4. And this is the output. So now let's see how we can solve this question. So the first brute force approach that I can think of is firstly calculating the length of the node. So firstly length will be 0, and after that what I will do, I will come up here like this is 1, this is 2, this is 3, this is 4, and this is 5. And after traversing this whole linked list, I will get to know that the length of this linked list is 5. Now after getting the length, what I need to find is the middle index, correct? So right now what I will do, I will simply take L and divide it by 2. So in Python, we will use integer division. So we will get 2, correct? So when we will get 2, we know that there is a node at this index. So if we see, usually the indexing is being done from 0. So this is 0 node, this is 1 node, this is 2 node. So at 2 we know there is the middle node. So we will again traverse this array and we will find the index which is present at this index, or we will find the node which is present at this index and we will return it. So this is the first approach, and this approach will take big O of n time and big O of 1 space complexity, but we are traversing this whole linked list twice in this approach. Not exactly whole linked list, but we are still traversing through this linked list twice. How? Firstly, we are traversing this linked list to calculate length. So for that, we are taking big O of n time. After that, we are again traversing this linked list to find the middle node. So for that, what we are doing, we are again doing n minus m traversal. So if we are going to solve this, we will get big O of 2n, right? And which will be big O of n at the end, and the overall time complexity will be big O of n. And as we are not using any data structure, that's why our space complexity is big O of 1. So let's quickly see the code of this approach, and after that we will see the optimization. So this is the approach 1, and I already coded this whole approach just to save time. So let's go through this code. So firstly, we are defining a variable header. With the help of header, what we will do, we will traverse this whole linked list and update our length variable and calculate the length of linked list. After calculating the length, we are finding the index by dividing it by 2. Now this integer division is beneficial in both ways. In the sense, like even if the length of linked list is positive or negative. Negative in the sense, not positive and negative, even and odd. So if the length of linked list is 5 or 6, for both it will work and give the exact value that we need. So once we get the index, we are again creating another variable, that is new header, and with this referencing variable, we will again traverse our linked list. And at the end we will return the exact node at which we ended this traversal. We are traversing this linked list for index greater than 0, right? Because we are decrementing it. So once this condition satisfies and we step out of this whole loop, we will be exactly at the same index that we calculated, and we will be at the middle node, so we will return it. So this was the first approach. Let's quickly run and test this. So we can see this is accepted. So now let's see the optimization. So in this approach, what we did is we are traversing this linked list twice. So can we do something else rather than traversing this linked list twice? So yes, we can do. So let's optimize this same approach and make it a bit more efficient. So for that, what we can do is, as we are traversing the linked list twice in order to get the middle node, right? The node which is present at that index. But what if, rather than calculating simply the length, we will store this whole linked list in a form of array? So what I am trying to say is, we will create another array, and in this array, what we are saying, traverse this linked list and store its node in this array. So like this will be first node, then I will go to this place, I will store 2, then 3, then 4 and 5. And this is how I stored the whole linked list, and I traversed it once. Now what I am saying is, simply return the mid element of this array. While I was traversing this linked list, I was not only maintaining the length, I was also maintaining the array, this whole array. So once I'll step out of this traversal, I will simply divide this L by 2 and return this index value from this array, right? So as the value was already there in the array, I don't have to traverse this whole linked list again. So in this manner, we optimize the traversal part. But now the time complexity is big of n, and space complexity is also big of n, because we are storing this whole linked list in an array. So in a way, rather than optimizing, we increased our space complexity. But yeah, this was another approach with which we can solve this question. So let's quickly check the code for this approach as well. So let me just comment out this approach. I have already coded the second approach as well. This is the second approach, where we define the array and stored the head. And then we are saying while array minus 1 dot next. So every time the last node will be pointing to the next upcoming node, right? So that's why we kept this condition where array minus 1 dot next. While this is true, we want our array to append with the next of this node, and at the end simply return the middle element of this array. So this was the second approach. Now let's quickly run and check this as well. So we can see that this is also accepted. Now let's go and optimize this solution even further. Now this approach that I am going to tell you right now, the third approach, this is the most optimistic one. So now let's see what this third approach is. Like in previous two approaches, what we were doing is we were firstly calculating the length, and then we were finding the index, and then we were returning the node which is present at that index. But now what we are saying, now we don't want to calculate the length, we don't want to traverse this linked list twice, but we just want to know what is the middle node. So how we can do that? So there is one approach, that is two pointers approach. Now if I'll say that there are 2 pointers where one is moving with 1 step and second one is moving with 2 steps, then we know that if this is traversing 5 steps in 5 seconds, so this second pointer is traversing 10 steps in 5 seconds, correct? So if I'll say that if I have 2 pointers and the second pointer is reaching the end first, then we know for sure the first pointer will be present at half of it, which is the middle node in this case, correct? So if we are going to use 2 pointers, this is the logic, where first pointer will be moving with +1, or only the first pointer will be taking only plus one step or only one step at a time, and second pointer will be taking two steps at a time. In this manner, the second pointer will reach the end first, and we will be sure that the first pointer is exactly at the center of this linked list or middle of the linked list. So we will return the node which is present at the first pointer position, right? So this is the third approach. So in this manner, we solve this question using three approaches, and this approach is of time complexity big O of n and space complexity big O of 1, in which we hadn't traversed it twice, but we just solved it using two pointers. So this was the third approach. Now let's code this approach as well. This one we are going to code it up in Python and Ruby. So let me just clean these previous approaches, or let me just comment it out. So we will define two pointers, that is slow and fast, and we are saying both are equivalent to head right now, but we need to traverse until and unless fast and fast dot next are present, because this condition makes sure that we are reaching end. We are not going any further. So what we will do, slow will be slow dot next, and fast will be fast, and fast will be fast dot next, and after stepping out of this loop we will return slow. So this was the whole code. Now quickly run this and check whether this is working or not. Okay, this is also accepted. Now let's code this approach in Ruby as well. So slow is equivalent to fast is equivalent to head, and we are saying while fast and fast dot next, inside this loop update slow with slow dot next and fast with fast dot next, and after stepping out of this loop simply return slow. Now let's check this as well. You can see this is also accepted. So these were the three approaches, and the first two one not the most optimistic one, but still they were a kind of greedy approach, and it is good for us to check all the approaches and then reach the optimized solution, because in this manner we will be able to prove that we don't have only the limited amount of knowledge. We have a whole overview of what the exact problem is and how to come up with a greedy approach, then optimize it a bit, and then reach a completely optimized solution. So these were the three approaches, and I hope this video was helpful for you all, and if it was, then don't forget to like, share and subscribe my channel. I will soon come up with more such videos. Till then, keep messing with algorithms, and thanks.